Hi everyone, and welcome back to physics. Today we're going to continue Newton's laws of motion, but we're really going to go over the first half of our guided practice of elevator physics. So let's get right into it. Now, elevators pose a little bit of a tricky proposition because you are accelerating or decelerating in the vertical direction. So it really kind of alters our normal force and how that works with our gravitational force, which we talked about in a prior video. We talked about if you're on a horizontal surface, our force of gravity is going to be equal to our normal force. So we're going to notice here, talking about when you're standing in an elevator, that that is not always necessarily the case. So if you haven't done this, I would suggest that you take a bathroom scale and you go into an elevator and you stand on it because it's quite fun to do. So you're standing on a bathroom scale in an elevator, and yes, people are staring at you, just in case you're wondering. It's not something normal to do, but I've done it and it's really enjoyable. Now it says that you weigh, it really should say that you have a mass of 50 kilograms. But the scale is going to read in newtons. So our first scenario, the elevator is at rest. So that's our first scenario. You're standing in the elevator, you just got in there, you put the scale down, you stand on the scale, and the elevator hasn't moved yet. So what is our weight or our force of gravity? Well, the elevator is at rest. So pretty simple. We do Fg equals mg. Okay. And the reason why I'm not going to do our given or our wanted and all sorts of things like that, because you don't have enough room in your packet, number one, and number two, you'll realize that we are going to be doing this quite often. So I'm just going to write down the equations and then plug in our substitutions appropriately. So let's solve for our weight force. We've got 50 kilograms. Our force of gravity, since we're on Earth, is 9.8 meters per second squared. So our answer turns out to be 490 newtons. Are the forces balanced or unbalanced? Okay, well, things we want to think about. If we are at rest, are we experiencing an acceleration? No. So we're not experiencing any kind of acceleration, therefore our forces are balanced because we're at rest, therefore no acceleration. Okay, not too shabby so far. Let's continue. Next question says, using the same information, draw a free body diagram of the forces acting on you while the elevator is at rest. Be sure to draw the size of your arrows appropriately. So, since we are at rest, here's our little dot. This represents us. Just for your reference, here is our elevator. There's the scale. And here's you. Just for a visual. It's not a very good visual, but it's a visual. So, first thing we want to think about, okay, what are the forces? Our first force would be our weight force. Our weight force always points straight down. Since we are at rest, since our forces are balanced, the force that is equal and opposite of that would be our normal force. So you want to make sure that our arrows are about the same size because they're equal and opposite. So we know that our normal force is equal to our negative gravitational force because we have balanced forces as opposed to unbalanced forces. What is the net force while the elevator is at rest? Things you want to think about here. Net force means what's our overall force? Since we have balanced forces, our net force must be equal to 0. Here's how we got this. Okay, so because we're at rest, balanced, and here's what this means. Our net force is equal to the difference between these forces. Our normal force, or our weight force, I should say, is equal to 490. And our normal force is also equal to 490. How did we get that? Again, we're dealing with balanced forces. Since we have balanced forces, they must be equal and opposite. Again, with our equation over here, the only reason why it's negative is because that's depicting that they're in opposing directions. Our free body diagram has the arrows depicting that they're in opposing directions. So, our net force is simply the difference between opposing forces. Therefore, we take 490 for our normal force, and we subtract 490 for our gravitational force, and we would get our overall net force of 0 newtons. Okay, so all of this is going on. Our weight force was easy to calculate. We figured out that we're dealing with balanced forces because we're at rest. Our free body diagram depicts that the forces are equal and opposite. And our net force is going to be 0 newtons because we have no unbalanced force here. And for the very last part of this question, it says the elevator is still at rest. What is the normal force? Well, we already figured that one out. It's going to be 490 newtons in the opposite direction. Okay? Pretty simple. Not too shabby. That one was easy because we're dealing with balanced forces. Now, because you're not just simply going to stand in an elevator, you don't just get in an elevator to not move anywhere. Well, some people might, but I certainly don't. I get in one to go somewhere. So let's try an example problem for what happens when we push the button to go to the top floor of a 21-story building, and the elevator begins to accelerate upward from rest at 2 meters per second squared. So, we still have the same mass, so let's figure out our gravitational force. So Fg still equals mg. So Fg equals our 50 kilograms. Our acceleration due to gravity is still 9.8. We're talking about our acceleration due to gravity here to give us our weight force. We're not talking about this particular acceleration. So our force of gravity remains the same at 490 newtons. Since the elevator is accelerating upward, this is where it kind of gets a little tricky. Does the normal force have to be greater than, equal to, or less than the force of gravity? Well, think about things. Think about how you feel when you're starting to accelerate upward in our little elevator. So here we are standing on a scale, we're accelerating upward. How do you feel? What does your body feel? You actually feel heavier. Your mass doesn't change, but because you're accelerating upward, your force with which the scale is pushing on you to move upward has to increase, which is why you are feeling heavier. Therefore, the normal force will have to be greater than our force of gravity. Again, since you feel heavier, the force with which you are pushed upward is greater than the force with which you are pushed downward. Are the forces balanced or unbalanced? Well, they're unbalanced, but here's why. You're accelerating. Anytime you're accelerating, you're dealing with unbalanced forces. So let's draw our free body diagram dealing with the forces that are acting on us. So we depicted that, and we just stated that our normal force is greater than our force of gravity. So our arrows must depict that they're unequal forces. So this free body diagram shows that, hey, yes, our normal force is in fact greater than our force of gravity. Again, you're accelerating upwards, you feel heavier, the force that's pushing you upwards has to be greater than the force that's pushing you downward. So what is the net force using Newton's second law? Well, the elevator is accelerating upwards. So let's go ahead and solve for this. Newton's second law, don't forget, is our F net equals ma. So our mass is 50 kilograms. But our acceleration is 2 meters per second. So F net equals 50 kilograms times 2 meters per second squared. F net equals 100 newtons. Now what does that mean? That tells us that the overall force that we are experiencing, because we're dealing with an unbalanced force, the overall force that we're feeling, the total force on our free body diagram, is 100 newtons. Okay, so things you want to think about, because we're going to draw our normal force in our free body diagrams. Things you want to think about. Looking at these two forces, knowing which one is going to be greater, which direction will our net force actually point in? Will it point up or down? Well, it's going to point, if you think about it in terms of like a tug-of-war, you're going to fall in the direction or be pulled in the direction of the larger force. So our net force points in the direction of the larger force itself. So if we just drew a free body diagram depicting our net force, we would have our net force pointing upwards with 100 newtons. So let's use that logic and figure out, okay, well, what is our normal force? So again, we've got our free body diagram here, our general free body diagram, and then our net force free body diagram. So we're going to just reiterate that, draw that right here. So we've got our normal force, we've got gravitational force, and we've got our net force, which we said was 100 newtons. We also said that our force of gravity was 490 newtons. So, figuring out and knowing that our net force is 100 newtons, what is the normal force? Well, it's going to be 590 newtons. And here's how we got that. Remember, to figure out our net force is the difference between two forces. So, if we had, so our net force is the difference between two forces. So we've got this. If our net force was 100 newtons, that's equal to Fn minus our 490 newtons. So we add 490 to both sides, and we would get our normal force equal to 590 newtons. Now, that's how you would mathematically do it. However, logically speaking, it makes sense. Since our net force is going to be pointing up, our overall force on that's acting on this object is 100 newtons and it's pointing up. That means that our normal force, since it is the greater force of the two, must be 100 newtons greater than our gravitational force. So now, what does the scale read as the elevator is accelerating upwards? Well, your force that scale is going to read always happens to be our normal force. Okay. So your scale will always read our normal force because that scale is what's going to be pushing you upward, which means our scale actually now reads 590 newtons. Your scale always reads your normal force. Always reads our normal force. So that's what's going on when you are accelerating upwards. So what I want you to do is pause the video, try part C on your own. There are a lot of questions for part C. There are questions 13 through 19, so go ahead, read it, make sure you read it thoroughly, and answer each section carefully. Once you've done that, you can come back and I will go over part C. Hopefully you paused the video and tried part C on your own. Now I'm going to go over the answers to part C and how to do this. So, again, you're still standing on a bathroom scale. You still have your same mass of 50 kilograms. But now the elevator and you accelerated for several seconds, and now you're moving upward at a constant velocity of 10 meters per second. Constant velocity is huge. Make sure you pay attention to that. So what is the gravitational force? Pretty simple. Our gravitational force hasn't changed and will not change unless our mass changes for some weird reason, which would be odd if you gained weight or lost weight on this tiny little elevator trip that you took. So Fg still equals 490 newtons. What is the acceleration of the elevator itself? So since we are moving at constant velocity, are we experiencing acceleration? Heck no, we won't go. No, our acceleration is 0 meters per second squared because we're moving at constant velocity. Are the forces balanced or unbalanced? Are we experiencing an acceleration or not? If we're experiencing acceleration, we're dealing with unbalanced forces. However, here, we're experiencing 0 acceleration. Therefore, our forces are balanced because we have no acceleration. Let's move on to question 16. It says here, to draw a free body diagram of the forces acting on you, be sure to draw the size of your arrows appropriately. So, we are dealing with balanced forces here. So our balanced forces mean that our arrows are going to be the same length. So our force of gravity, which is equal to 490 newtons. Our normal force still points straight up. I'm pretty sure by now you probably figured out what your normal force is equal to. Let's figure out what the net force is using Newton's second law. Well, the elevator is moving at constant velocity. Okay, so F net equals ma. We stated earlier that our acceleration is equal to 0 meters per second squared. So if we plug in our mass of 50 kilograms and 0 meters per second squared, we should get a net force of 0 newtons, which makes complete sense because we have no unbalanced force acting here. Therefore, the difference between these opposing forces should be 0. I just wanted to show you that yes, the net force, if you use Newton's second law, will still come out to be 0. So now, let's try question number 18. What is the normal force? Things you want to think about. Because we're dealing with equal and opposite forces, because we have our free body diagram over here depicting what is going on. We've got our gravitational force is equal to 490 newtons. Our net force is equal to 0. Therefore, our normal force, which is opposing our force of gravity, must be equal and opposite. So Fn must equal negative Fg. In other words, if we're dealing with a depiction here, our normal force must be 490 newtons in the opposite direction. What must the scale read while the elevator moves up with constant velocity? Remember, our scale will always read our normal force. And since our normal force is equal to 490 newtons, that's what our scale will read. So while you're accelerating upward, you feel heavier, your scale will read heavier because we're dealing with unbalanced forces. Now, because we're dealing with constant velocity, we're dealing with balanced forces. We're not dealing with any unbalanced forces. Our scale will read our normal weight force of 490 newtons, which it's going to read because that weight force happens to be equal to our normal force, which is what our scale is giving us. I hope this made elevator physics a little more clear. So, if you have time, you can begin watching the next video. If not, you can just sit back and relax for a little bit. And I hope you enjoyed it, and I will see you for our next video.